Continuing on with our roots and radical expressions, we're going to start Chapter 6, Lesson 1. It's very similar to what we did in the Chapter 6 review, the intro to Chapter 6. So I want to kind of talk about this key concept, and it looks a little confusing in words, but it's going to be clear with the examples. So if a to the n equals b, then the nth root of b equals a. That exponent n can be anything. And so just a to that n power, the way we kind of undo that is with the nth root of that b would equal a. So here's kind of the key concepts. If your exponent n is odd, there is one real root and only one real root. If your exponent n is even and b is positive, there are two real roots, the positive and the negative. So the positive root would be your principal root, and then the negative root is its opposite. There's always the two real roots if n is even. Now, that's if b is positive. If b is negative, there are no real roots. And we kind of discussed that with imaginary numbers, because we can't take the square root of a negative number. Well, we can't take the fourth root or the sixth root or any of those even numbered roots. We cannot take that of a negative radicand. Okay, so here's the examples. List of odd exponents right here. Okay, so just kind of showing you, if 3 to the third power is 27, then the cube root of 27 has to be 3, because the positive cube root, since 27 is positive, my cube root also has to be positive. Negative 3 to the third power, notice, equals a negative 27, because this basically represents negative 3 times negative 3 times negative 3. And if I'm going to multiply negative 3 times negative 3, I get positive 9. And then positive 9 times negative 3 is negative 27. So there's where our odd exponents kind of change things. We can have a negative answer with an odd exponent. So therefore, the cube root of negative 27 has to be negative 3. We can actually take the cube root or the fifth root of a negative number, unlike an even root. So here's our next example. The cube root of negative 64 equals negative 4, and the cube root of positive 64 equals positive 4. Those are your examples of one and only one real root. Here, on the even exponents, okay, we get 3 squared equals 9, but notice the square root of 9 is 3 and negative 3, because we can also say negative 3 squared equals 9. So that's why we have two real roots if our b is positive. So for example, the next one is negative 4 to the fourth power is positive 256. Well, therefore, the fourth root of 256 is going to be 4 or negative 4. I still get both of those real roots. And then our next example, our last example, is the fourth root of negative 64. There are no real roots. There are only imaginary roots. We'd have to take that I out and then take the fourth root. So that's kind of the main difference. We've been working with square roots and those types of things. So just kind of keep in mind as we move into cube roots and fourth roots and fifth roots that you are going to have odd exponents and even exponents, and they work just a little bit differently when we are taking those radicals or those roots, those third roots, fourth roots, fifth roots. Okay, so that's kind of the basics of what I wanted to start. So let me move down the page. So example 1, what is each real number root? Again, this is something that we've kind of been doing, just kind of want to keep it what we're working on here and just take it a little bit further into third roots and fourth roots. So the cube root of negative 8 would be negative 2, because negative 2 times negative 2 times negative 2 is negative 8. So these are also the kind of things you can type into the calculator. This will not give you a syntax error on my calculator because it can be done. However, looking at letter B, if I try to do the fourth root of negative 1, it's going to give me a syntax error. So in this case, we're just going to write no real solutions. There are only imaginary solutions, so no real solutions. For problem C, it's the opposite, or the negative cube root of negative 125. So I'm going to write this negative out here. However, the cube root of negative 125 is negative 5. So now when I take the opposite of that cube root of negative 125, I end up with a positive 5. So pay attention to those negatives. And then right here, we have the square root of negative 2 squared. So there's a couple ways you can go about that. You can understand that the square root of anything squared, basically the radical sign, the square root, and the squaring are inverse operations. They just kind of cancel each other out, so to speak. Or you can go ahead and write it like this so that you can see what's going on. Because negative 2 squared, the quantity negative 2 squared, really translates to negative 2 times negative 2. And then if we simplify that, we get the square root of positive 4. And technically, we would come up with our 2 solutions. If we were to solve it just like this, we would probably say, well, the square root of negative 2 squared is just going to be negative 2. So in this case, this would be your more expected answer because of those parentheses under the radical. Okay, so let's look at the next property. So for real number a, the nth root of a to the n power, okay, here's what we're looking at. Okay, it's just a if n is odd. It's the absolute value of a if n is even. So if you're taking an even root, like this square root, 4th root, 6th root.
Angelina O'Keefe and Yesenia Rodriguez, please contact the office.
Sorry, she just wanted to get it on the video. So if you're taking the square root, 4th root, or 6th root, your root of your variable is going to be the absolute value, the variable only. Okay. If you're working with cube roots, 5th roots, 7th roots, it is just going to be your variable is basically because of that only one real solution and the 2 solutions. And why that is our variable has to be positive when it comes out. Okay, so when it comes out of the radical, because of we'll talk about that because you can't have a negative under the radical. So let's go ahead and simplify this one. So my square root of 16x to the 8th, my square root, so the square root of 16 is 4, and my square root of x to the 8th basically would look like this, would be x to the 4th. Now, I've got those absolute value signs there, but I'm just going to say that no matter what my x value is in this case, x to the 4th is going to come out positive. Remember, absolute value means we have to have a positive number. Absolute value is always a positive number, so we have to have a positive number. X to the 4th is going to be a positive number. So that we don't necessarily need the absolute value signs in this case. So we could technically just simplify this to 4x to the 4th. Okay? All right, let's look at problem B. This is the 4th root. So again, it's an even. My n is even, so I'm going to take the 4th root of these. I want you to think about when we did square root up here, we took my x to the 8th, and basically we divided my exponent by 2, because this is an understood 2, square root. Okay, so we divided by 2. So x to the 8th divided by 2 became x to the 4th. Well, since I'm now dealing with a 4th root, what I'm going to actually do is since my exponents here are divisible by 4, I don't have to break them up. If they're not, we'll talk about that in a second. Okay, so x to the 8th, well, my exponent of 8 divided by 4 is what I'm going to do. And my y is going to be my exponent of 12 divided by 4, which is going to simplify to, well, 8 divided by 4 is 2. And 12 divided by 4 is 3. So this simplifies to x squared y to the 3rd. Now, the x squared does not need absolute value signs. Why does my y to the 3rd? Okay, this is where it gets a little tricky. X squared is always going to be positive. So even if x ended up being negative 2 times negative 2 is positive 4. However, if y were negative 2, okay, negative 2 times negative 2 times negative 2 is negative 8. I cannot have a negative under my radical. So the y value cannot technically be a negative. This will come into play later on when we're solving radical equations. So just keep that in mind. The absolute value really, really matters once I've taken that even root and I have an odd exponent come out. Okay, and we're just going to practice. So, problem C, cube root. Not going to have to deal with the absolute value. Yay, it's kind of nice not to deal with the absolute value. However, I'm going to do the same process. 6 and 9, my exponents under the radical, are both divisible by 3. So that means these are both perfect cubes under our cube root radical. So I'm going to have a to the 6th divided by 3, and I'm going to have b to the 9th divided by 3. Well, this comes out to be a squared, and this comes out to be b cubed. No absolute value needed because I can have negatives under that radical. Okay? All right, so continuing on, problem D. This is the square root. Again, that's the understood 2 there. It's a square root. X to the 5th is not a perfect square, so I'm going to break that into something that is a perfect square. Times that 1 left over x. Okay, x to the 4th times x is x to the 5th. Y to the 6th is a perfect square, so I don't have to break that up. X to the 4th comes out to be x squared. Y to the 6th comes out to be y cubed, and again, odd exponent, so I need the absolute value signs. And then what's left under the radical would just be the x. Okay, the absolute value, don't let it get to you. As we practice it, you'll understand it. You'll have to really pay attention to it with even roots and then your variables. Okay, so let's move on to, oh, it's your turn. Guided practice. So 6.1 was all about simplifying radical expressions, especially with cube roots and fourth roots and fifth roots, and getting on to those things beyond just square roots. 6.2 is going to be about adding, subtracting, multiplying, and dividing radical expressions, whether it be square root, cube root, fourth root. Just keep in mind that, again, we're going to be dealing with all those different types, and the rules, you'll understand, they kind of apply across the board to some degree. So simplify a radical expression involving addition and subtraction. The first thing I want to point out is this right here. Like radicals with the same radicand, and that also means the same root. So in other words, they all have to be a square root, a cube root, a fourth root. They all have to be the same radical with the same radicand. Can be added and subtracted. Now, keep in mind, it's kind of like the radicand is kind of like a variable. Your radicand has to be identical for you to be able to add or subtract it. Just like with a variable, we can add x's together, we can add or subtract x squareds together. As long as our radicals and exponents are the same, our variables and exponents are the same, we can add. Well, the same thing with radical expressions. If our radical is the same and our radicand is the same, then we can add those together. So for example, part A is a square root of 2 plus 4 square roots of 2. So just like a variable, this is like an understood 1. We have 1 square root of 2 added to 4 more square roots of 2 for a total of 5 square roots of 2. Very, very basic. And if it were the same thing with our variables under the radicand, it would work the same way. So let's look at problem B. Notice we have the square root of 3 in each of our problems, or each of our terms. So we can add or subtract these together because our coefficients don't necessarily matter. Our radical expressions, our radical parts do. So 5 square roots of 3 minus 3 square roots of 3 is 2 square roots of 3. So if we simplify this, we end up with 2 square roots of 3. And then we're left with minus 6 square root of 3. Well, 2 minus 6 is negative 4 square root of 3. The square root of 3 just tags along just like if it were an x or a y or an x squared or any other variable. That square root of 3 just kind of tags along with its coefficients. Now, let's look at problem C. I notice that we have a square root of 8 and a square root of 2. Those radicands are not the same. However, the square root of 8 can be simplified. There's a perfect square factor of 4. Okay, so if I simplify this one first, and I take that square root of 4, and I go ahead and pull that out front, take the square root of it, multiply it by 2, I end up with 2, and my square root of 4 becomes 2, and I'm left with a radical of 2. And then I continue to simplify, and 2 times 2 is 4 square roots of 2 plus 5 square roots of 2 equals a total of 9 square roots of 2. Okay, again, let's look at problem D. I have the square root of 3 and a square root of 2 and a square root of 2 and a square root of 3. None of those can simplify any further, so I can combine my square roots of 3, and then I can also combine my terms that are square root of 2. So let's do the square root of 3 first. 8 square roots of 3 plus 1 square roots of 3 is 9 square roots of 3. And then 4 square root of 2 times 1 square root of 2 would be, times 1. 4 square root of 2 minus 1 square root of 2 is 3 square root of 2. I cannot go any further with this. These are not like terms at this point, so that's as simple as I can make it. I cannot do the 9 minus 3 because I do not have exactly the same radicand. Okay, so let's go ahead and look at problems E and F. All right, so we have 5 square roots of 3 plus 4 square roots of 12 minus 2 square roots of 75. Well, again, I notice that I don't have the same radicand, but I do have some perfect square factors. So I can break the square root of 12 into 4 times 3, and I can break the square root of 75 into 25 times 3. Okay, so I've broken it into my perfect squares here. Perfect square of 4, perfect square of 25. So my 5 square roots of 3 is going to stay. I'm going to take the square root of 4, which is 2, and I'm going to multiply that. So like that's done. 4 times 2 is 8, and then the square root of 3. Okay, the square root of 25 becomes 5. So I do 2 times 5, and I get 10 square roots of 3. Now all of my 3 terms have a square root of 3 in them. So I now can combine them. 5 plus 8 is 13, and then 13 minus 10 is 3 square root 3. Okay. All right, problem F. Distributive property. So I'm going to take this square root of 2 and I'm going to multiply it times all 3 terms inside that parentheses. So the square root of 2 times 5 square roots of 8. So again, remember that I'm going to be multiplying the radicands. We cannot add radicands that are not alike, but we can multiply anything. So my coefficient of 5 just gets to come out front, and then the square root of 2 times the square root of 8 becomes the square root of 16. And yes, I'll simplify that in a minute, but let me do my multiplication first. Okay, my negative 8, again, just comes down. My coefficient comes down. The square root of 2 times the square root of 18 becomes the square root of 36. My 12 just comes down, and the square root of 2 times the square root of 2 is the square root of 64. So now I notice that I have all perfect squares. So this becomes 5 times 4 minus 8 times 6 plus 12 times 8. Okay, and notice I took the square root of 16 for the 4, the square root of 36 for the 6, and the square root of 64 for the 8. So 5 times 4 is 20, 8 times 6 is 48, and 12 times 8 is, it's a plus, isn't it? 12 times 8 is 96. Okay? So I need to add all those together. So 20 minus 48 becomes negative 28. And then negative 28 plus 96 would be, let's see, 68. So when I simplify that expression, I get a nice no radical number of 68. I hope I did that correctly. If I did any math incorrectly, please let me know. All right, let's talk about multiplying first. So, combining radical expressions as products. So I want you to we've already done this, so we just did it on problem F. So this shouldn't be that difficult. We've been doing it. This should all be review. Let's talk about this. Can we multiply the following expressions, y or y not? So I want to start with G, and I want to ask, can we multiply those together? I don't want you to jump into this too fast and just go. This is going to be the cube root of 12 or the square root of 12. Notice I have one cube root and I have one square root. Okay? At this point, we cannot multiply those together the way they are written. Now, we'll learn a way we can multiply those together later. But right now, I just want to make sure that you're paying attention to whether you're dealing with cube roots, square roots, or fourth roots. Those type of things. Pay attention to that part. So in this case, right now, the way this is written, we cannot multiply these because they are not like radicals. All right, so let's go on to problem H. Since we do have like radicals, we have both of them being the cube root. We end up with the cube root of negative 4 times 2, which is the cube root of negative 8, which we have already discovered is negative 2. Okay? Same thing down here. We've done this, but now we're going to just do it with the cube root and the fourth root, which changes it up just a little bit. It doesn't change it up much. I'm still going to do my coefficients multiplied together. I'm still going to add my exponents, and then I'm going to simplify. Now, I could go ahead and simplify my cube root of 8 out of that second radical, and I could simplify the 16. Or I can multiply them together and do that all at the end. So let's go ahead and do that. So the cube root of 16 times 8. Well, let's see. 8 times 10 is 80. 6 times 8 is 48. 80 plus 48 is 128. Okay? I believe that's correct. 48 and 80. Yes. Okay. My x squared, see, this may be easier to simplify first. My x squared times my x to the 4th becomes x to the 6th. And my y to the 4th times y to the 5th becomes y to the 9th. Remember, we add exponents when we are multiplying. We add exponents. Okay? And that might be something we might need to review. When we multiply, we add exponents. When we divide, we subtract exponents. And when we have a power to a power, that's when we multiply, and we'll talk about those later. So now I can go ahead and simplify. I'm not sure about cube roots of 128. I think 64 goes into 128, and 64 has a cube root of 4. So I believe it's, so we're going to change this to the cube root of 64 times 2. Okay, my x to the 6th is a perfect cube because 6 is divisible by 3. My y to the 9th is a perfect cube because 9 is divisible by 3. So I'll take the cube root of 64. I'm going to get 4. I'm going to take the cube root of x to the 6th. I'm going to get x squared because, again, I'm doing 6 divided by 3. My cube root of y to the 9th would be y to the 3rd because I'm doing 9 divided by 3. Yet I still have, and this is where you got to make sure you can tell it's a cube root and not a cube somewhere else, I still have a 2 left under there. Okay. Okay, let's go ahead and do problem J. Notice this is a fourth root. This is a fourth root. So I'm going to have the fourth root. I'm going to do it the same exact way. 8 times 8 is 64. Okay. X to the 3rd times x to the 4th would be x to the 7th. Okay. Y squared times y to the 3rd is y to the 5th. Again, add your exponents. That looks like a 1. I don't want it to look like a 1. Okay. So now I need to do the fourth root of 64. So we have to think, is there anything that is a fourth root? Like I think 4 times 4 times 4 is 64. And then 2 times 2 times 2 times 2 is just 16. So I can't think of anything that's like 64 is not a perfect fourth root. However, 16 goes into 64 4 times. So I know 16 is a perfect fourth root. Again, you guys have calculators you can do this on. So I know that 16 times 4, I know 16 is a perfect fourth, however you say that. Now, I need to break my x into parts that are divisible by 4. So this x to the 7th is going to have to be x to the 4th times x cubed. Okay, so I've got to make it into, and that's kind of what I had here. Again, I could have simplified first, but I'm kind of showing you because a lot of people are going to want to do it this way, multiply and then simplify. I'm going to take my y to the 5th and I'm going to break it into y to the 4th times y. Again, I have to break it into exponents that are divisible by whatever my root is. Since it's a fourth root, I need exponents divisible by 4. Okay, so now just to show you, this is a perfect fourth root. This will be a perfect fourth root, and this will be a perfect fourth root. So everything else that I'm going to put in green will have to stay under the radical. Okay? So as I bring these out, the fourth root of 16 is 2. The fourth root of x to the 4th is just x, because 4 divided by 4 is 1. The fourth root of y to the 4th is y, because 4 divided by 4 is 1. And that leaves me with, a fourth root of my 4, my x to the 3rd, and my y. And that is simplified. Okay, so that's why I wanted to do these. I know we've been doing these, but they are a little different when you talk about cube roots and fourth roots, and they just take practice, which is why we give you homework. All right, the very last property I want to talk about today is quotients, dividing. So here's our next property. If I didn't go over the last property, I'm really sorry, but it's pretty simple. You'd already done it. So this property we have not really done a whole lot of. If the nth root of A and the nth root of B are real numbers, in other words, we don't have any imaginary numbers involved. So if the nth root of A and the nth root of B are real numbers and B does not equal 0, then the nth root of A over the nth root of B can also be written as a radical of the nth root of that fraction A over B. So we can go both ways with this. If something is written like this, we can always divide it up and write it like that if we need to for some reason. So this goes back and forth. Either way works fine. So let's go ahead and simplify a quotient. We can go ahead. I'm going to go ahead and do this because it will be easier if we simplify first and then try to take the square root. And we're starting with square roots. So this is where I'm going to talk about the dividing. So I'm going to go ahead and do 18 divided by 2, and I'm going to get 9 in my numerator. And then I'm going to kind of refresh your memory on this. Here's how I teach this when I teach it in Algebra 1. I ask myself, where do I have more of my variable? Do I have more x's in the top or the bottom? Well, I have 5 x's being multiplied in the top and 3 x's being multiplied in the bottom. And I don't want to have to write those out and show how they cancel. So I just ask myself, where do I have more, in the top or the bottom? And I have more in the numerator, so my x is going to stay in the numerator. And then I'm going to ask myself, how many more do I have in that numerator? I have 2 more because I have 5 in the top and only 3 in the bottom. So however many more I have in the numerator, that's my new exponent. So basically I'm doing 5 minus 3. It's always the numerator's exponent minus the denominator's exponent. So 5 minus 3 tells me that I'm going to have x to the positive 2. Well, I divided out my 2 in my denominator and made that 18 and 9. I divided out my x cubed, so I don't have anything left in my denominator. I just now have I have 9x squared in my numerator. And My radical is still there. So now I have a much easier way to take the square root. The square root of 9 is 3, and the square root of x squared is x. Okay, same thing with cube roots. I can rewrite this as the cube root of this whole thing, 162 y to the 5th over 3y squared. So I'm going to simplify this. Okay, and 162 divided by 3 is 54. My 3 is now gone. I have more y's in my numerator, so my y is going to stay in my numerator. And I have 3 more y's in the numerator, so that's my new exponent. Notice everything here. I don't think 54 is a perfect cube, but I think 54 can be broken into a perfect cube. 27 times 2. 27 is a perfect cube, 2 is not. So 27 is a perfect cube, y cubed is a perfect cube, 2 is going to stay under the radical. So this becomes the cube root of, how about I take the cube root first. The cube root of 27 is 3, and the cube root of y cubed is y, and then I can do my cube root of what's left, which is the 2. So 3y times the cube root of 2. Okay, again, takes some practice, but it's not super difficult. Simplify your fraction first to maybe something a little bit more easy to work with. All right, the very last thing, I thought dividing was the last thing, but the very last thing is rationalizing the denominator. And I have 2 examples for that. Okay, when we say rationalize the denominator, it means just like we talked about there. When we did imaginary numbers, we said there could be no I in our denominator. Okay, same thing here. There can be no radicals in the denominator. Okay, and no denominator in any radical, which goes back to writing it like this. Okay, so we can't have like that. Okay, that would be a denominator in a radical. So we can't have a radical in the denominator or denominator in the radical. Cannot. So we're going to rationalize the denominator. Well, all we have to do, we learned here that if we did the square root of x squared, that just becomes x. So if we will just multiply, I'm going to rewrite this. I'm not going to rewrite it with one big radical sign because I'm going to multiply my numerator and my denominator by my radical that's in the denominator. Okay, so let's see what happens here. So the square root of 2x times the square root of 3x gives me the square root of 6x squared in my numerator. The square root of 3x times the square root of 3x, well, that's just like the square root of 3x squared. So the square root of 3x squared, so that just becomes 3x. My radical disappears. We could solve it, and we can know that would be 9x squared, but then when I take the square root, I get 3x. Now, I can simplify this a little further because I can take the square root in the numerator. I can take the square root of x squared. So I have x, and then the square root of 6 is left because I went ahead and took the square root of this part. And then I have 3x in my denominator. And then the very last step, what's the last thing I can do? Guess what? Those x's divide out, leaving me with the square root of 6 over 3. Now, a radical in the numerator is just fine. But this right here simplifies to that right there. Notice the variables disappear. Now, we could have done that. We could have simplified it. If we put this all under the radical, like this, we could have gone ahead and simplified. Let me change color so you can see it. We could have said the x's cancel out, leaving me with the square root of 2 over the square root of 3, and then we could have rationalized from there. Either way works. I just want you to know how to go about doing it. So, since we can't really simplify anything here, I'm looking at this cube root. I know 5 and 12, nothing simplifies. X squared, y squared, z, none of that simplifies. So I'm going to rewrite this, and then I'll show you. So 5x squared, and then the cube root of 12y squared z. So I'm going to multiply my numerator and my denominator by 12y squared z, the cube root. I'm multiplying by a form of 1, because any time you have something, you know, when you just have the same thing over, this is like a form of 1. If I divide that out, it would be 1. I'm not changing my expression at all. I'm not changing the value of my expression. So let's do the numerator. I end up with the cube root. 5 times 12 is 60. X squared, well, there's no other x's, so the x squared stays. Y squared stays, and z stays. Because there's nothing, I have no like variables, so they just all go under the radical. Down below, guess what happens here? You know what I forgot to do though? Oh, let's start over on this one.